So right now, this lesson we're talking about elastic potential energy. So as you can tell, we're talking about something that is stretchy. Elastic could be applying to like a spring or an elastic that you're talking about. So let's just review what we have done so far. Okay, we know that all work done are based on the change in energy. And then in terms of mechanical energy, we have talked about two kinds. We have talked about the kinetic energy, which is when an object have a speed, it has some energy that's in there. And then we've also talked about gravitational potential energy. And if we ever lift anything high up, if it has some sort of height, it stores some sort of energy. Okay? And today we're going to talk about the elastic potential energy. That's calling if we ever stretch or compress either a spring or an elastic. Well, you can't compress an elastic. So this is mostly talking about a spring. It actually stored up energy as well. And today we're just learning the equation of how to calculate the stretch. Okay? So if I have an elastic, a regular elastic here, okay? This is called the equilibrium position. And when it's at an equilibrium position, it doesn't have any elastic energy. Okay? Like it's just being stored up. But if I take the time and I stretch it out, first of all, the amount that I've stretched it out, we call it the delta x, and it's measured in an SI unit of m. So the distance that you've stretched it compared to when it's equilibrium, not stretching it out, is called the delta x. This is now energy stored up. So if I let go of an elastic, what happened is it will actually start moving or start shooting at your friend. Please don't hurt people's eyes. But you know what I'm saying, right? You would be able to store it up and it can actually do some work later on. And that's what we're talking about. Okay? And so we're talking about a spring. So if this is a spring that is at equilibrium, is not stretched or is not compressed. If I compressed it, we always still would talk about the distance between the length as it is delta x, or vice versa, opposite to that. If I stretch it out, the same spring, if I stretch it out, what happened is the amount that it got stretched out compared to the equilibrium is called delta x, and that's the distance compared to when it's not stretched or compressed. So the first law that we're going to look at is called the Hooke's law. Hooke's law basically tells you that the force that is exerted by an elastic device, so a spring, we're going to be using spring for the rest of the course. It's either when it's stretched or compressed, the amount of force is equals to kx. So imagine it, if I have a really flimsy, like if I have a really flimsy spring, versus say your car coil. I don't know if you've ever seen a car coil that is like super stiff. Okay, and if we're talking about the equation, f equals k times x. Basically, what your k stands for is basically how stiff or how flimsy it is. If it's like a super flimsy spring right here, I only need very little bit of force to be able to get it stretched quite a bit of amount. But if I have a really stiff spring, I will need a much bigger force to be able to stretch it the same amount. So basically the K, the spring constant, is telling you how stiff or how flimsy the object is. Okay, so K stands for spring constant. The unit for that is newtons per meter. You can work it out from the equation. If I rearrange the equation for K, it's F over X, or the change in X. F is measured in Newton, X is measured in meters, and that's why the unit for the spring constant is newtons per meter. Okay, and if we have any springs that actually follow the Hooke's law, meaning if I increase the force, I should stretch it further, we call those the ideal spring. Okay, this is this is like a multiple choice question. Okay, so any springs that obey the Hooke's law, we call that the ideal spring. I don't know if you've ever dealt with an elastic. If you overstretch it, like say if you use an elastic and you tied it on a humongous jar, and then what happened is it won't go backwards. Like it won't go back and strength back when you take it off. That's when you break the ideal spring law and it's no longer proportion to the force that's applied. Okay? So now we're working on what is elastic potential energy. So the equation for elastic potential energy is work equals to 1/2 kx squared. Okay, and they used it from the graph called velocity x graph. So basically, if things that follow the ideal spring constant, like the Hooke's law, what happened is as I increase the x, I would increase the force. When I increase the x, I increase the force. So it goes like that. And then the work done, it always worked on basically the area under the curve. That's how you found it. So because they found that it's a triangle, so work equals to 1/2 kx squared. And so work is energy transformation. So in here, they would have gotten EE equals to 1/2 kx squared. If you have time, you can watch the Slinky Drop YouTube video just talking about bungee jumping and other exciting applications of it. I can link it in the classroom post as well. Okay, so an example. A student stretch a spring horizontally for a distance of 15 millimeters, that's your x, by applying a force of 0.18 Newton to the east. Determine the spring constant. So recognize spring constant means K. And then what is the force exerted by the spring on the student? So what is the force exerted by the spring on the student? Okay, so student is stretching the spring. So they gave me x is equals to 15 millimeters. Hopefully you're good to convert that in meters. You divide it by 1,000. And so make sure that's the only trick to the question. They gave you the force. So the student is pulling it at 0.18 meters. Newtons to the east. So force is kx. 0.18 is k times x. Rearrange your equation. So 12 newtons per meter, meaning whatever this spring is, it will take 12 newtons to be able to extend or compress it by 1 meter. Okay, so part B asks you, what is the force exerted by the spring on the student? So the student pull 0.18 Newton east. So how is the spring pulling on the student? So part B is asking, is basically a third law type of question. So action reaction force. So that means the spring has to be pulling 0.18 newtons to the west direction on the student. A ball with a mass of 0.075 kilogram is hung from a vertical spring and is allowed to stretch slowly from its unstretched equilibrium until it comes to a new equilibrium position of 0.15 meters below the initial one. Determine the spring constant. Okay, so let's just start with that. Okay, so what they're saying is the spring is supposed to be this long when it's not hanging onto anything. But now if we put a mass of 0.75, so if I hooked onto a mass that is 0.075 kilogram, what happened is it is able to stretch it with a distance, so delta x is 0.15 meters. Okay, so they're saying determine the spring constant. So I want K, so I know that I'm dealing with elastic force, elastic force. So free body diagram is what you need to look at. So right now it's a balanced equilibrium position. So it's like a first law type of question. If I have force of gravity pulling downward, but at the same time I'm going to have the elastic force that is pulling it upwards. So F net equals to MA. So we're still tying to the force. Net force, the acceleration of the system is 0. right? Because right now it's just staying there, is not moving. So that means the two forces should be balanced. So Fe minus Fg is equals to 0. Rearrange the equation. Fe would have to be equals to Fg. And to solve for Fg, we know that the equation for that is m times g. And we've learned today that the equation for Fe is k delta x. So now I can just plug in what I know and then solve for my k. So k delta x is 0.15, mass is 0.075, and the g is 9.8. So multiply it out, 0.075 times the 9.8, and then I would divide 0.15 to get an answer of 4.9 Newton per meters. Part B. If the ball is returned to the spring original equilibrium position and then allowed to fall, what is the net force on the ball when it has fallen 0.71 meters? So now this question has slightly changed, is no longer in the equilibrium balance positions. Okay, so it's letting you know that you still have your Fg acting on the object, but this time your Fe would have changed because your delta x, instead of 0.15, that was completely stretched. We're only stretching it a bit less, so 0.071 is how much it has stretched. And then I would go about and find out what is my net force. So the object is accelerating downward, so F net equals to ma down, which is Fg, minus up, which is Fe. It equals to ma. But I actually don't even need the ma because I'm solving for the F net, so it's mg minus k delta x, so it's equals to the mass times 9.8 minus the k you found, which is 4.9, and then times 0.071. So 0.075 times 9.8 minus 4.9 times 0.071. So I got 0.39 Newton, and this is going downwards. The overall net force is down. And then finally, part C, we're looking for the acceleration of the object when it's at 0.71. So it's basically what we've done over here with the MA. I'm actually solving for my A now. So I know this is running out of room. I'm going to do it on the side here. So this is part C. I know F net equals to MA, and we found F net to be 0.39 equals to the mass times the A. So 0.39. So use whatever value. I would use 0.3871, just like all the time. I know someone's going to ask, do I use the 0.39 or do I use what's in the calculator? I would use back what I used from my calculator and then divide it by that, by the mass. So I should have an acceleration of 5.2 meters per second square going down. I'm still watching my SIGDIC. I'm still watching my directions, and I'm still watching my units. Okay, last question. An apple of a mass of 0.1 kilogram is attached to a vertical spring with a spring constant of 9.6 newtons per meter. The apple is held so that the spring is at its unstretched equilibrium position, then it's allowed to fall. So it was at unstretched first, and then it was allowed to fall. Neglect the mass of the spring and the kinetic energy. How much elastic potential energy is stored when the apple has fallen 11 centimeters? Okay, so I got the mass. So 0.1, and I have the spring constant, which is K, 9.6 Newton per meters, and I have also delta X. So it was from unstretched and now has fallen 11 centimeters. Please watch your SI unit. We always convert it into meters. So 11 centimeters is 0.11 meters, and they're asking for what is the elastic potential energy. So the equation for elastic potential energy is 1/2 kx squared. And So I just straight plugged it in. The only thing is make sure your unit is correct. Common mistake is sometimes we forgot to square, but that's pretty much it. So pretty straightforward. So 0.5 times 9.8, 6 times 0.11 square equal 0.058 joules.